Thank you for your kind introduction. I am going to present some recent studies on the mechanisms leading to the stratification of positive column plasmas in rare gases. My co-workers on this study are Professors Dosbalayev, Orazbayev, Bufendi and Ramazanov from Kazakh National University in Almaty. Most of the results I am going to present have been very recently published in Physics of Plasmas, these references. This is the outline of my talk. After a short introduction, I will discuss the possible mechanisms leading to the stratification of a positive column plasma in rare gases. In a third part, I will show results from a particle-in-cell Monte Carlo collisions model that has been used to describe the formation and dynamics of striations. Then I will show how one can understand the mechanisms responsible for the instability by linearization of a fluid model of the plasma. And in a last part, I will illustrate the theoretical results with experiments and particle simulation in a capacitive radio frequency discharge. This is a typical picture of a DC discharge with striations in a positive column. The presence of striations in discharge tubes has been known for a long time, since Faraday. Striations can form in a variety of conditions depending on the nature of the gas, current, pressure, and tube radius. The mechanisms responsible for the stratification of the plasma are still not fully understood. These mechanisms can be related to stepwise ionization, Coulomb collisions, transport terms in moment equations, and so on. The aim of this talk is to clarify these mechanisms in the case of rare gases. We can try to describe the formation and dynamics of these striations with a one-dimensional model. If we consider that the plasma is quasi-neutral, we can write this simple ambipolar diffusion equation with ionization. The Laplacian term can be split into an axial component and a radial component. We can put the radial component on the right-hand side of the equation, so we get this expression. In the axially uniform and steady-state regime of the positive column, the left-hand side is zero and ionization must balance the radial ambipolar losses to the walls. The radial profile is a Bessel function. We can define nu W as the frequency due to ambipolar losses, and we get this simple one-dimensional axial equation for the positive column where the ionization frequency depends on the electron mean energy or temperature and the loss frequency is given. We also need to write an energy equation for the electrons because the ionization frequency and ambipolar diffusion coefficient depend on electron temperature. To look for possible instabilities, we do a perturbation in plasma density and electron temperature. We linearize the equations with respect to this small wave perturbation of the form written here. Omega is the complex frequency, k is the wave number. Little omega is the real part of the frequency and gamma the imaginary part. Gamma is the growth rate of the perturbation. And there is an exponential growth of the perturbation if gamma is positive and the system is not stable. If we inject these perturbations in the continuity equation above, we get the growth rate as a function of wave number. I am not going into the details. One gets this expression for the growth rate. In this expression, the first term is related to axial ambipolar diffusion, and it is negative. As expected, diffusion is a damping term. The second term is proportional to the derivative of the ionization frequency with respect to electron density. This term is zero if ionization is only due to direct ionization of the neutrals. It can be positive and non-zero in the case of stepwise ionization. This can trigger instabilities. The sign of the third term depends on the signs of the ratio delta T E over delta N, so it is related to electron energy transport. We can have instabilities if an increase in electron density leads to an increase in electron temperature. This is not at all intuitive, and we need to write an energy equation for electrons to study the sign of this term. Before addressing this question by linearizing the equations, I want to show how particle-in-cell simulations can help describing the stratification. We consider a one-dimensional particle model with periodic boundary conditions. This is a standard particle-in-cell model where collisions of charged particles with neutral atoms are described with a Monte Carlo algorithm. An electric field E0 is applied to the plasma column, which means that the field E0 is superimposed to the space charge field obtained from Poisson's equation with periodic boundary conditions. So, the average electric field in the column is imposed and is equal to E0. The ionization rate in the column is the results of E0 and of the self-consistent space charge electric field. In a positive column, ionization is balanced by the charged particle losses to the walls. So, a simple way to describe this in the model is to do the following. Each time a given electron undergoes an ionization event in the Monte Carlo module, an electron-ion pair is generated at the location of the incident electron, and one electron and one ion are randomly and separately removed from the simulation. Doing this, the total number of electrons and ions does not change in time, and the average plasma density is constant. So, the simulation is quite simple. This also means that the column radius is not imposed, but is a consequence of the choice of E0. I am going to summarize the results. This figure shows, at a given time, the axial profiles of charged particle densities on top, electric field in red, and temperature and ionization rate in the bottom of the figure. This is argon with an applied field of -3 volt per centimeter at 0.1 torr. We'll see that at this pressure metastable ionization is negligible. The column length is 10 centimeters. The average plasma density is 10 to the 15 per meter cube. We see some quite large amplitude oscillations of the plasma density. The total electric field presents large peaks separated by ambipolar regions. The electron temperature is only slightly modulated, while the modulation of the ionization rate is much more important. This is because the relaxation length of low-energy electrons is much longer than the relaxation length of electrons with energy above the excitation and ionization thresholds. It turns out that in rare gases the potential drop between striations is quantified and is related to the excitation energy thresholds. This is true in experiments and simulations. Here the potential drop is about 11 V, which is close to the energy excitation threshold in argon. These types of striations are called S striations. This movie shows the time evolution of the instability. The electron and ion densities are in the top figure. The electric field is represented with the red line. This is still argon at 0.1 torr, with an average electric field of -3 volt per centimeter in the plasma column. The striations move without deformation from the anode side to the cathode side with a velocity on the order of 1.4 kilometers per second in these conditions. It is very interesting to look at the spatial distribution of the electron energy distribution function, which is shown here for argon. The color plot shows color contours of the distribution function as a function of energy and position. The main properties of the EEPF are that 1. There is a strong modulation of the tail of the distribution. 2. We clearly see some bumps in the distribution. The separation between bumps is related to the potential drop between striations and to the excitation energy thresholds. And 3. There is a large population of low-energy electrons at the positions where the electric field is low and where ambipolar diffusion is important. These electrons are trapped in the ambipolar field. Between ambipolar field regions, electrons are accelerated by the large peaks in electric field associated with the abrupt potential drop, and this generates the bump of the distribution. Here, for example, we see that the low-energy electrons are extracted from the ambipolar region and form a kind of electron beam which loses its energy in the next ambipolar region. Considering the electron distribution that we have just seen, it is clear that a fluid model cannot describe properly the nonlinear, saturated regime of the instability. However, the conditions that are responsible for the development of the instability can be characterized and understood with a fluid model, provided that the shape of the electron distribution function in the uniform regime prior to the development of the instability is properly taken into account. The model we used is adapted from a model developed in the group of Miles Turner in 2005 and more recently in this paper by Desangles and colleagues published in PIL 5 years ago. In this model, we linearize the equations for electron density, temperature, and metastable density. This gives a dispersion relation from which we can obtain the growth rate, angular frequency, and wavelength of the instability. Here are the fluid equations for electron transport assuming quasi-neutrality. This is the continuity equation where gamma E is the electron flux defined by an axial ambipolar diffusion term proportional to the density gradient. One can also write an energy equation with an energy flux H sub E. The energy flux has a term proportional to the temperature gradient. This is the well-known thermal conductivity term. On the right-hand side, we have a first term related to Joule heating and a second term related to energy losses due to collisions, mainly inelastic collision with neutrals. The energy loss per unit time L epsilon is a function of the electric field, just like the ionization frequency μI. They both increase with the electric field. The constant terms gamma 0 and H0 correspond to the fact that there is an electron current in the column. The energy flux is often written like this in fluid models, with a temperature gradient term and a thermal conductivity coefficient kappa E. But more accurately, there should be another term in the energy flux, proportional to the electron density gradient with a coefficient chi E that we will call the thermoelectric Dufour coefficient. Chi E is related to the difference between the electron diffusion coefficient in energy and the diffusion coefficient in space. For a Maxwellian distribution chi is 0. This is the reason why it is often neglected. But the electron velocity distribution in a positive column in noble gases is far from a Maxwellian, so chi is non-zero. The continuity and energy equations can be linearized for small variations of plasma density and electron temperature. I am not going into the details of the derivation, but this is not very complicated. We have seen already that the continuity equation gives the growth rate of the perturbation gamma with a negative, damping term, a second term proportional to the derivative of the ionization frequency with respect to electron density, and a third term proportional to delta T over delta N. The linearization of the energy equation gives the ratio delta T over delta N, which is written here. To have an instability, the growth rate gamma must be positive. This is possible if the ionization frequency increases sufficiently fast with the electron density. The growth rate can be positive also if delta T E over delta N is sufficiently positive, which implies that chi be sufficiently negative. It turns out that the Dufour coefficient can indeed be negative in rare gases. I have plotted here the electron energy diffusion coefficient multiplied by the mobility ratio and the electron diffusion coefficient as a function of electron mean energy. This is done with the Boltzmann-Solver-Bolsig plus. The Dufour coefficient is proportional to the difference between these two terms. This is the case of argon. We see that the electron diffusion coefficient is significantly larger than the other, so that the Dufour coefficient chi E is always negative in this range of electron mean energy. This is characteristic of this kind of shape of the electron distribution function, which is far from a Maxwellian. Now we look at the derivative of ionization frequency with respect to electron density, which also appears in the expression of the growth rate. This term can be non-zero and positive when metastable ionization is present. So we must develop a model for metastable production and ionization. We use the simple argon chemistry model summarized here. We consider electron-argon collisions with elastic collisions, direct excitation, and ionization. Direct excitation includes excitation to the most important metastable state. We also include stepwise ionization of the metastable and electron quenching, as well as associative ionization or metastable pooling. Here is the equation for production and losses of the metastable. Production by direct excitation, loss by stepwise ionization and electron quenching, and by associative ionization and losses to the walls. The total ionization rate is the sum of direct ionization, stepwise ionization, and associative ionization. By linearizing the metastable equation and the electron continuity and energy equations, we can calculate the different terms of the growth rate. Here is plotted the calculated growth rate in argon as a function of pressure times radius of the positive column. This is the growth rate when metastable ionization is not taken into account. We see that instabilities and stratification can exist at low pressure if metastable ionization is not present. This is the consequence of the negativity of the Dufour coefficient chi in the electron energy equation. There is no striations above about 1 torr centimeter when metastable ionization is not present. When metastable ionization is included in the model, the domain of instabilities and striations is extended up to several torr centimeters. The results show that metastable ionization becomes dominant above about 0.5 torr centimeter. This can be seen on this figure, where we have plotted the fractional ionization rates due to direct ionization, stepwise ionization, and associative ionization as a function of pressure times radius. But if we analyze the different terms of the growth rate, we find that, under conditions where metastable ionization is dominant, the stratification is still due to the negativity of the thermoelectric Dufour coefficient. In other words, the nonlinearity of metastable ionization is not responsible for stratification and is actually negligible. Now I am going to show some results from experiments and particle simulations. The experiment is performed in a 13 MHz radio frequency capacitive discharge in a 20 cm long glass tube with a 1.1 cm radius in argon. Because of the radio frequency field, the striations can be standing if the discharge is perfectly symmetric. We studied the presence of striations as a function of pressure and power. We looked at the effect of the presence of a small percentage of hydrogen on the stratification of the plasma. Hydrogen is a good quencher of metastable argon. We also performed one-dimensional particle-in-cell Monte Carlo collision simulations of a bounded radio frequency plasma. In this model, the charged particle losses to the walls are given by this classical expression. The loss frequency for a 1 cm radius column is on the order of 510 to the 4 per second at 1 torr and is inversely proportional to the gas pressure. The same metastable model, as described previously, is included in the simulation. The experiment and simulations are described in this paper. Here we see the standing striations in an argon-positive column at 13 MHz for different gas pressures. There are very clear striations at low pressures. The wavelength of the striations is on the order of 3 cm and slightly decreases with increasing pressure. And the standing striations tend to disappear above 2 torr. Adding hydrogen to argon has practically no effect at 0.1 torr, even for hydrogen percentages as large as 10%. At pressures above 1 torr, the stratification disappears with a small percentage of hydrogen. This means that metastable ionization does not play an important role at low pressures. At higher pressures, metastable ionization is dominant, and if we destroy the metastable argon by adding hydrogen, only direct ionization is present and the striations disappear. This is consistent with the theory that we have just discussed, and which says that there is no stratification above 1 torr centimeter when metastable ionization is not included, black line. Now I will show very briefly some results of the particle simulations. This slide shows the space distribution of the time averaged electron and ion densities, electric field and plasma potential, and electron mean energy and ionization rate. This is argon at 0.1 torr for conditions close to the experiment. We have well-defined striations in these conditions. The wavelength is consistent with the experiments. The electron mean energy is slightly modulated while the ionization rate is very strongly modulated. In the RF case, the electron energy distribution function at steady state is less complex than in the DC case. Here we see the effect of metastable ionization on the electron density at 3 different argon pressures. The blue lines correspond to particle simulations without metastable, and the red lines correspond to simulations with metastable included. At 0.3 torr, the results is practically independent of the presence of metastable. At 0.8 torr and above there are no striations if metastable ionization is not included, as we can see by comparing the blue and red line on the bottom plot. We performed simulations with a modified argon chemistry in such a way that the metastable ionization rate is linear with electron density. We did that by cancelling stepwise ionization and increasing associative ionization. We found very similar results in that case. This confirms that metastable ionization is necessary for stratification at pressure above 1 torr, but that the nonlinearity of metastable ionization is not responsible for stratification. I will conclude with these few points. Many known features of striations in positive columns in rare gases at low current and pressure can be reproduced with a simple 1D particle model. The stratified regime of a DC positive column needs a kinetic description, but the mechanisms responsible for the instability can be clarified by linearization of a fluid model. The negativity of the thermoelectric Dufour coefficient in the electron energy flux is responsible for stratification. This coefficient is negative because of the non-Maxwellian nature of the electron energy distribution function in the uniform electric field prior to the instability onset. The consequence is that a small increase in plasma density leads to an increase in electron temperature, leading to a growth of the instability. Failures of previous attempts to clearly understand the mechanism triggering the instability is due to the fact that the Dufour term is generally neglected in the energy equation, which is a good approximation only for Maxwellian distributions. The negativity of the thermoelectric Dufour coefficient is responsible for stratification even when metastable ionization is dominant. This means that the nonlinearity of metastable ionization is not responsible for stratification. Thank you for your attention.